Hello everyone, and welcome to this exam revision webinar for MT1173 algebra. What we're going to be focusing on today is solving exam style questions. And I'll be doing that live so that you get more examples of how to write and structure your answers in the exam. And so as a warm-up here, we have a question on Cramer's rule. So we have this linear system here, 3 equations in 3 unknowns. And it is given here that this system has a unique solution. And in particular, we're going to use Cramer's rule to solve it. And so let me now just give this coefficient matrix A a name. And then we have the vector of unknowns X and then the right-hand side B. And the first thing we do is to work out the determinant of A. Let me do, say, a first row expansion here. You are free to choose. Remember also the relationship between the signs of minors and cofactors for a 3 by 3 matrix. And so we get 1 times, because the 1 here is in a plus position, and then we cover up the column and row containing this 1, and then we take the determinant of the 2 by 2 submatrix left here, and we see that this is -2 minus 0. Then we have -1, because this 1 here is in a minus position, times the determinant of the 2 by 2 matrix we get when we cover up the column and row that this 1 is in. So we get 2 times -2 minus 0 times 1. So it's just -4 minus 0. And finally, it's +1. Then cover up the column and row that this 1 here is in and take the determinant of this 2 by 2 matrix. So it's -2 minus 1 times 1. And now we just add all of this up. We see that the determinant of A is -1. And so Cramer's rule is all about calculating determinants. And so now we construct the matrix A1, where we replace the first column of A by the right-hand side vector B. We find the determinant of A1. Let me say use the third column here. Since that has a 0 in it, it will reduce the calculations. Again, remember, so third column, plus, minus, plus are the signs here. So it's 1 times, then cover up this column on the first row. So it's -4 plus 4. Then it's technically -0 times. We'll just put ... That gives us 0 anyway. And then it's, well, I wrote plus, but it's plus and then -2. So let me write -2 directly, since that is in a plus position, the sign doesn't change. And then we cover up this column and this row. Take the determinant of this 2 by 2 matrix, that's 5 minus 4. And all of this gives us -2. Now Kramer's rule tells us that the value of x that solves this system is given by the determinant of A1 divided by the determinant of A. And so x is 2. Now we proceed to finding the value of y that solves the system. Now the second column of A is replaced by the right-hand side vector. As before, we find the determinant. Let me do a third column expansion again. You are free to choose. Here's going to get 1 times -8 -4 -0 times ... And then we have -2 times 4 -10. And we get -12 plus 12, which is 0. So y is given by the determinant of A2 over the determinant of A. And so y is simply 0. And then finally, to find the value of z that solves the system, we replace the third column of A by the vector B, find the determinants of this matrix. Let me say do a first row expansion here. And we get 1 times -4 plus 4. Completely fine if you just want to write 0, but I just want to be clear with the calculations. Then it's -1 times -8 -4, and finally it's +5 times -2 -1. And so z is given by the determinant of A3 divided by the determinant of A. And so z equals 3. And of course, we can verify that this result is correct by substituting x equals 2, y equals 0, and z equals 3 into each of the original equations in the system to verify that we get the right-hand side. So we can leave that as an exercise. Now, moving on to this linear system here, we have 3 equations and 5 unknowns, and 2 tasks here. First, to find the reduced row echelon form of the augmented matrix of this system and explain why the system is consistent. And then part 2 will be to find the general solution of this system, expressing your answer in vector form. So let me give you a head start there on writing down the augmented matrix and starting your elementary row operations and aiming for reduced row echelon form. just take care here that we transfer the numbers accurately. We see here that we have a leading 1 in the first row here. And now we want to create zeros below that leading 1. And so that determines our row operations. We see that if row 2 goes to row 2 plus row 1, well then this minus 2 will become 0. And if row 3 goes to row 3 minus row 1, well then this 1 here in the third row will become 0. And then the other entries of row 3 will just change accordingly. So take a moment to work ahead a little bit and notice here, very important, I'm doing elementary row operations to row 2 and row 3 in one go, you can say, in the sense I don't need to do row 2 and then write down the resulting matrix and then do the operation to row 3 and then write down the resulting matrix. So this saves me some writing, but we do need to keep the row 1, which we're using to add or subtract multiples of to rows 2 and row 3. Need to make sure that this remains fixed. That's very important. Otherwise, we are most likely going to violate the system here. So adding row 1 to row 2, just add the 2 up. And then deduct row 1 from row 3. Now we see here that we have a leading 1 in row 2. And so now we want to create zeros above and below this leading 1 as we make our way to the reduced row echelon form. So we keep row 2 fixed. We see that if row 1 goes to row 1 minus row 2, and row 3 goes to row 3 minus row 2, then we're going to get zeros above and below the second leading 1. If we want, we can write down first the row we are keeping fixed. That is our new row 1. And now we see here that we have a final and third leading 1 in the third row. And now one more step is needed here to get to reduced row echelon form. We need to create zeros above it. And so now we keep row 3 fixed. And then we, in this case, we deduct 1 times row 3 from row 1 and row 2 respectively. Just move all of this a little bit to the left. And now we are in reduced row echelon form. Now we want to answer why this system is consistent. And the easiest way to argue that is that the rank of AB is equal to the rank of A, which we see here. There are 3 leading ones in the augmented matrix, which is the same as the number of leading ones in A. And now to the second part. Now we want to write down the general solution of the system in vector form. Let's have a little head start on that, just to see where you stand at this point of your revision. And the idea there is not to put you on the spot, but rather if you're stuck, then let's get you unstuck while we're here in this session. And as you've probably already noticed here, the leading ones are in the first, third, and fifth column. And so we treat x2 and x4 as free parameters. And so we can let x2 equal s, where s is some real number, and let x4 equal t, where t is some real number. And remember, when we look at our reduced row echelon form of the augmented matrix, well, this corresponds to a system of equations. The equations in the original system have changed, so they're not the same anymore, because we have done elementary row operations to them. But what these two systems have in common is that they have the same set of solutions. So the first line here tells us that x1 minus x2 plus 0x3 minus x4 plus 0x5 equals 1. And so rearranging that now for x1, we have that x1 is 1 plus x2 plus x4, but x2 is s and x4 is t, we said. So x1 is 1 plus s plus t. x2 is s, x4 is simply t. Then we look at the second row here of our reduced augmented matrix. This tells us that x3 is minus 1 minus 2x4, but x4 is t. And so x3 is minus 1 minus 2t. And then looking at our third row here, well, this simply tells us that x5 equals 2. And now we write this out as a position vector on this two-dimensional flat plus scalar multiples of the two direction vectors. And where s and t here are real numbers that can take any value. So this would be our answer to part 2. Now, I do want to point out here how to check your answer. So that you get confidence when you are practicing. Also, let's just point out the solution set is a two-dimensional flat in R5. But now the question is how to check our answer. So this is just an extra here. Maybe I can write it in a different color. So P here satisfies all three Cartesian equations defining the linear system. Meaning if we plug in x1 equals 1, x3 equals minus 1, and x5 equals 2 into each of these equations, you will get the right-hand side. And when it comes to these direction vectors, well, they are orthogonal to each of the normals of the hyperplanes in the original system. And let's write down those normal vectors. You're simply looking at each equation here. x1 minus x2 plus x3 plus x4 plus 2x5 equals 4. That's the first equation, and so on. The corresponding normal then, just take the coefficients of x, y, x1, x2, x3, x4, x5, like this here. So the second equation there has normal minus 1, 1, 0, 1, minus 1. Then finally, the third hyperplane there has normal 1, minus 1, 2, 3, 4. Okay. And when we say that D1 and D2 are orthogonal, well, how do we check that? Well, that means that the dot product of D1 with each of these normals is 0. So D1 dotted with this vector will give you 0. D1 dotted with this normal will give you 0. And D1 dotted with the third normal here will give you 0. Similarly for D2 dotted with each of these normal vectors in turn. So this way, it's very quick to check your answer. Now, moving on to the next question. Consider this linear system here, 3 equations and 3 unknowns, where we have some constants A and B appearing here. And the set of solutions depends on the values of A and B. So first task here is to write down the augmented matrix of the system, and then by performing a few elementary row operations on your augmented matrix as needed, determine the values of A and B, if any, for which this system is inconsistent, consistent. The solution set is a line in R3, and the system has exactly one solution. So we write down the augmented matrix as instructed. We aim for reduced row echelon form, but we need to know when to stop here, and we'll see that soon. So have a head start on that. Okay, so first thing is to create zeros below the first leading one. And so we see that if R2 goes to row R2 minus row 1, And R3 goes to R3 minus A times row 1. Then that will achieve that aim. So we're keeping row 1 fixed. And then we are deducting or adding multiples of row 1 to the other rows. Notice here we don't know the value of A, but no problem. If it's 0, we're not doing anything to row 3. If it's non-zero, well, then we are deducting A times row 1 from row 3. We see here that we have a leading one in the second row. So creating zeros above and below. We get now the following. And now we need to stop here because we don't know the value of A. But now we are ready to analyze. So have a look at this reduced augmented matrix and have a think about, are there any values of A and B for which this system is inconsistent? Meaning that it has no solution. There is no common point or line or plane, as it were, in R3 of intersection is what it means to be inconsistent. So what would this third row look like then? And we talked about a condition for consistency in the previous question. The system is inconsistent if the rank of the augmented matrix AB is equal to the rank of A plus 1, meaning that there will be one more leading one here in the augmented matrix than in the coefficient matrix here. Because then we have a final row here, 0, 0, 0, something non-zero, which corresponds to an equation of the form 0x1 plus 0x2 plus 0x3 is something non-zero. And there aren't any values of x1, x2, and x3 that can satisfy that. And so let's see when this happens. Well, if 1 minus 5a is 0, and b minus 4a is not 0, which is the same as saying if a equals 1/5 and b is not equal to 4/5, well then the system is inconsistent. It has no solution. Now, how about consistency then? Are there any values of AX equals B for which the system is consistent? Well, we already said what the consistency condition is. The rank of the augmented matrix has to be equal to the rank of A. And have a think about that. That splits into two cases here. I'll give you some time to think about it. So like I said, it splits into two cases. The rank of the augmented matrix equals the rank of A. Well, either the rank will be 2, so the number of leading ones is 2. That means that the third row will have become a row of zeros. So if 1 minus 5A is 0 and B minus 4A is 0, so if A is 1 over 5 and B equals 4 over 5, then we have a consistent system. So in that case, we have rank 2. And the other possibility then is that A is such here that we get another leading 1 here, which means that in the most general terms, and so a common mistake would be to only state a subcase, which to say that 1 minus 5A has to equal 1. So that's a leading 1 there in the third row. But more generally, it cannot be 0. That's the only condition. Because anything non-zero, let's say 1 minus 5A is 13. Well, then the next step will be to divide row 3 by 13, and then we will have our leading 1. So that's the most general condition. If 1 minus 5A is non-zero, okay, then the coefficient matrix here has 3 leading ones. Is there any condition on the right-hand side then and on B? No, there isn't. So then B can be anything. B can be any real number. So if A is not equal to 1/5, then the system is also consistent. And then we have rank 3 in the augmented matrix, and which is equal to the rank of A. And now we need to answer if there are any values of A and B for which the solution set of this system is a line in R3 have a think about that. And when does that happen? Well, we've already discussed that case above here, actually. If A equals a fifth and B equals 4/5, well, we have a consistent system and we have rank 2. So there's one free parameter in the system. So a line is, of course, a one-dimensional flat in R3. So then we have a line in R3. So we have consistency, one free parameter. And finally, is it possible for this system to have exactly one solution? We see here that we have covered that above as well. When we have consistency and rank 3 here, A is not equal to a fifth, well then this matrix here has full column rank. In this case, it's a 3 by 3, so it's a square matrix, so then A is invertible, and we have a unique solution. But more generally, for a non-square matrix, then we have full column rank. And consistency here, then there is a unique solution. So I mean that A has full column rank. Okay. That wraps up question number 3. Now let's move on to the next question. In R5, find a Cartesian equation of the hyperplane that passes through the point 1, 2, 3, 4, 5 and is parallel to these 4 vectors you see here. D1, D2, D3, and D4. And so in other words, saying that these vectors, the hyperplane is parallel to these vectors, is the same as saying that these di are the direction vectors for the hyperplane. Remember that the hyperplane in R5 is a 4-dimensional flat. And so a vector parametric description for the hyperplane will have 4 direction vectors, linearly independent, of course. And so recall in general terms that the hyperplane in Rn is an n-1 dimensional flat. And what is the Cartesian equation of the hyperplane? It's given by the following. A general vector x dotted with a normal to the hyperplane equals a position vector, or point, if you like, on the hyperplane dotted with a normal to the hyperplane. I'm just going to call the hyperplane H here. And so this is what we are looking for. We already have P, so all we need is to find a normal n to the hyperplane. And so think about how these direction vectors for the hyperplane are related to the normal. That's the key here. Once we have figured that out, then we are well on our way. So just have a think about that. What I want to remind you of here is that n satisfies that n dotted with a direction vector for h gives us 0, because the normal is orthogonal to the hyperplane. Now, of course, we cannot visualize in R5, but it is orthogonal, therefore, to each of the direction vectors that span the hyperplane. So that's how we define orthogonality. That the dot product between these vectors give us 0. And now we can use a matrix method to find them. And if we take the direction vectors, put them as rows in a matrix, and we find the null space of this matrix, that precisely will give us a normal to the hyperplane. So setting it up like this is precisely setting up for each d here, n dotted with d equals 0. And so the null space here, the solution set, will be one-dimensional And we can take any non-zero scalar multiple of the single vector that will come out here. Now, I'm not going to do the row operation here. I'm just going to give you here the row reduced echelon form. So if we call this here AX equals 0, well, then this is the reduced row echelon form. Obviously, the right-hand side stays 0 throughout. And so we see here 4 leading ones. X5 is a free parameter. And so a resulting vector here. X1 is 0. X2 is a half t. X3 is a third t. X4 is minus t. And X5 is t. And if we want to work with the vector now without fractions, we can. Any non-zero value of t here will give us a normal vector, right? So any non-zero scalar multiple is an equally good choice. There aren't any unique answers, but if we choose t equals 6, then that will get rid of the fractions. And now we just use the formula here to write down a Cartesian description. That is a single Cartesian equation for the hyperplane. So a general vector x on the hyperplane dotted with a normal equals a point that we were given here on the hyperplane dotted with a normal. And now it's just a matter of multiplying out here. And the right-hand side there. Gives us 18. And this here, now we've precisely refreshed, if you needed it, why you can read out the normal from the coefficients of x1, x2, x3, x4, and x5 here. Because this here is precisely the equation of the hyperplane. So we talked about that earlier when we talked about that each of the equations in a linear system is a hyperplane in whatever dimension we are in. In Rn, it's an n-1 dimensional flat. Now, on to the next question. So we have a linear transformation T from R3 to R3. defined by the properties that t of the vector 2, 2, 2 gives us the vector 3, 3, 3. And the kernel of t is such that x plus y equals 0. So it's a single Cartesian equation there for the kernel. And let's focus on part A first. Find a basis for the kernel of t. So have a think about that. Let me give you a head start. And as a hint, if you haven't already thought of it, well, we have a Cartesian description for the kernel. And if we find a vector parametric description for the kernel, then that will give us the basis vectors we need. So think about how to go from Cartesian description to a vector parametric description for the kernel. And to go from a Cartesian description to a vector parametric description, we solve the system of linear equations that make up the Cartesian description. In this case, it is only one equation, so it's one restriction on 3 variables. There are 2 free parameters here. Obviously, in this case, Z has to be chosen to be free. And we can choose either X or Y to also to play the role of the second free parameter. However, let me emphasize the method here. If we take this equation and we write it in matrix form and then create the augmented matrix, it's going to look like this here. Now this is already in reduced row echelon form. So nothing other than what we did before. We treat here y and z as free, since the leading variable here is x. So let y equal s, where s is any number, and let z equal t. Where t is any real number, then a vector parametric description for the kernel of t And again, we just look at this single row here. X plus y equals 0. So x is minus y, but y is s. So x is minus s. Well, y is s and z is t. So this is a vector parametric description for the kernel. And we know that the Gauss-Jordan method guarantees that these direction vectors are linearly independent. And so a basis for the kernel of T is therefore, let's call it B subscript T. Is the set consisting of these two vectors. Remember that a basis for a vector space is a linearly independent set that spans the vector space. And now we want to determine the dimension of the range of T and find the basis for the range of T. So have a think about that. In particular, you can work at the dimension of the range of T by recalling the rank nullity theorem for linear transformations. So have a think about that for a moment. And the rank nullity theorem tells us that the rank of T plus the nullity of T is equal to the dimension of the domain of T. And just pointing that out here, obviously here the linear transformations from R3 to R3, but if these two are not the same, then it's the domain of T, the dimension of the domain of T here. That is relevant. And the dimension of the range of T is equal to the rank of T. Which is equal to the dimension of the domain of T minus the nullity of T. We've already seen that the nullity of T, the dimension of the kernel of T, is 2, since a basis for the kernel contains 2 vectors. And so the dimension of the range of T is 1. And moreover, we're given the piece of information that 333 is in the range of T. Therefore, a basis for the range of T is, you can either take the set containing the single vector 333, or equivalently vector 1, 1, 1. Now the question has two more parts. It says now let AT equal C1, C2, C3 be the matrix that represents T where the Ci denotes the ith column of AT. Using your basis of the kernel of T and the fact that T of 2, 2, 2 equals 3, 3, 3, derive a system of equations for the column C1, C2, and C3 that allows you to find these columns and hence the matrix AT. And let's recall here what the basis for the kernel and range were that we derived on the previous page. We need the basis of the kernel of T. And the key here is that the basis vector in the kernel and the fact that the kernel of T is equal to the null space of AT, that will give us a linear combinations of the columns of AT equal to the 0 vector. And so we see that minus C1 plus C2 equal the 0 vector. And that is C2 equals C1. So that's the first equation. Then also A times a second vector there in our basis for the kernel is equal to the 0 vector, which tells us that C3 is simply the 0 vector. So that's equation 2 that we want to work out. And now we can update. So far we know that AT will be C1, C1 as a second column also, and then the 0 vector as the third column. And we also know that t of the vector 2, 2, 2 gives us the vector 3, 3, 3. And so in other words, AT times the vector 2, 2, 2 will give us 3, 3, 3. And now writing AT as C1, C1, and the 0 vector. Now we get the third equation. That 4 times C1 equals the vector 3, 3, 3. In other words, C1 is a vector with 3/4 as each entry. And now we can write down our matrix AT. And then we have one more part. Find an invertible matrix P and a diagonal matrix D such that AT equals PD, P inverse. And now I chose this question on purpose here to highlight these concepts and the links between the information that we have already been given. Now, usually, if we were just given this matrix A T here that we just found, let's say we're given that and said diagonalize A, means find the eigenvalues of A and then find the eigenspaces corresponding to each eigenvalue and so on. Well, that will be the traditional way of diagonalizing by starting from A and then finding eigenvalues and corresponding eigenspaces. But I claim here that we have enough information to diagonalize A with what we've already done. So let's just pull that together. And in particular, to diagonalize AT, we need a basis, call it B of R3, consisting of eigenvectors of AT and their respective eigenvalues. And I claim here that one of the eigenvalues of AT is 0. And let's see why. So for each non-zero vector v in the kernel of T, which is equal to the null space of AT, we have AT times V equals a zero vector by definition of belonging to the kernel of T and in the null space of A. And that is equal to 0 times V. And so each non-zero V in the kernel of T is stretched by AT by a factor of 0. Obviously, for basis vectors, we are only interested in non-zero vectors. And we can therefore deduce that that basis for the kernel that we found is a basis of a two-dimensional eigenspace of AT corresponding to eigenvalue 0. And moreover, since we know that T of 2, 2, 2 is equal to the vector 3, 3, 3, AT times 2, 2, 2 is 3 over 2 times the vector 2, 2, 2. And so 2, 2, 2 is stretched by AT by a factor of 3 over 2. So either the set here 2, 2, 2 or equivalently 1, 1, 1 is a basis of a one-dimensional eigenspace of AT corresponding to eigenvalue 3 over 2. And so the basis B of R3 consisting of eigenvectors of AT can be taken as the following. And now we can write down our invertible matrix P. We simply put these vectors from our basis B as the columns of P. And notice here that once we have committed to this ordering of the eigenvectors, then we have no freedom in how we write D, because now you have to have the corresponding eigenvalue. So the first two vectors are eigenvectors of eigenvalue 0, and the third column here is an eigenvector of eigenvalue 3 over 2. So this ordering absolutely matters. And then we have AT equals P D P inverse. So that brings us to the end of this revision webinar. So with that, I want to wish you a productive revision period. Good luck with your forthcoming exams. And I hope you've enjoyed the course and that you enjoy the rest of your degree program here with us at the University of London with LSE. So thanks again for joining today and have a great day. Thank you.